Every time you tap your phone, click a mouse, or check your watch, you're communicating in a secret language, a language you might not even know you're speaking. Today, we're going to pull back the curtain and decode it. This is all about the secret language of machines, digital electronics. Let's dive in. And it all really boils down to this one kind of mind-blowing question. Think about it. Every single photo, every video, every complex app on your phone, it's all built from just two little symbols. How on earth is that possible? Well, stick around because that's exactly what we're going to figure out. So here's the game plan for today. We'll start with the secret language itself. Then we'll check out the four most important dialects of that language. After that, we'll see how they handle tricky things like negative numbers, look at a super safe system called gray code, and finally, we'll make you a translator. All right, let's start at the very beginning. To understand how computers think, you first have to understand how they count. And that foundation, the absolute bedrock of all digital electronics, is the idea of a number system. So what in the world is a number system? It's really just a set of rules for writing down numbers. The most important part is what's called the base, or radix. That just tells you how many different digits you get to play with. This one little idea, it's the key to everything else. Now here's where it gets interesting. In the digital world, we don't just use one number system. We actually use four main ones that all work together. You can think of them as our digital Rosetta Stone, the key that lets us translate between the way we talk and the way machines talk. First up, you've got decimal, that's base 10, the one we use every day. Then you have binary, base 2. That's the real language of computers, just zeros and ones. But these other two, octal and hexadecimal, they are absolute game changers. Think of them as cheat codes for us humans to make reading long binary strings way, way easier. And this is the magic right here. For a computer, it's not about abstract numbers. It's about electricity. A 0 literally means off, or a low voltage. And a 1 means on, a high voltage. It's a physical switch. That's it. Simple, powerful, and it's what makes everything work. Okay, check this out. This table really shows you what's going on. Just take our good old number 10. For us, it's 1, 0. But in the binary language, it's 1, 0, 1, 0. In octal, it's 12. And in hexadecimal, it's just A. It's the exact same value, just written in four totally different languages. And this is why we need those shorthands I was talking about. Look at the number 187. In binary, it turns into this monster. Seriously, can you imagine trying to find a typo in a line of code that looks like that? No way. That's exactly where octal and hexadecimal come in to save the day. All right, new challenge. Computers can count positive numbers, no problem. But what about negative numbers? How does a system that only knows on and off even understand the idea of less than 0? Well, the solution is pretty clever, and it's called signed and unsigned numbers. Here's the trick. With unsigned numbers, it's straightforward. Every bit helps represent the value, so they're always positive. But with signed numbers, they do something genius. They sacrifice one little bit, the one all the way to the left, the most significant bit, to be the sign guy. If it's a 0, the number's positive. If it's a 1, the number's negative. Let's walk through an example together. Don't worry, it's just a process. Take the number 101. Step 1, look at that first bit. It's a 1. So right away, we know we're dealing with a negative number. Step 2, we flip all the bits. 101 becomes 010. Step 3, just add 1. So 010 plus 1 is 011. And what's 011 in binary? It's 3. So because we saw that 1 at the start, our final answer is -3. See? Not so bad.
Okay, now for something I think is just plain cool. You see, standard binary is fantastic. It's the workhorse. But in some cases, especially with physical sensors, it can actually cause errors. So to fix that, some very clever engineers came up with a special system called gray code.
The whole idea behind gray code is beautifully simple. It has one rule. When you go from one number to the very next, like from 7 to 8, only one single bit is allowed to change. That's it. It sounds like a tiny detail, but that one little change makes a huge difference in making systems more reliable. And you can see exactly why right here. Look at going from 1 to 2 in normal binary. 2 bits have to flip at the exact same time. But what if 1 is just a little bit laggy? For a split second, the machine might read a totally wrong number. But with gray code, only 1 bit ever flips. There's no race, no confusion, just a clean, safe transition every single time. All right, we've met all the different languages. Now it's time for you to become the translator. This skill, which has the fancy name Radix Conversion, is absolutely essential for anyone who wants to really understand how digital systems work. Whoa, okay, I know this chart looks like a lot, but trust me, it's your new best friend. It's basically a master cheat sheet. All you do is find where you're starting and where you want to go. So if we want to go from binary to octal, we just find the intersection and boom, there's our rule, group bits in threes. Easy, right? Let's give it a shot. Okay, time to put this into practice. We're going to take a binary number and translate it into its octal shorthand. And remember the rule from our chart? It's super simple. We're just going to bundle up the bits into groups of 3. The only trick is you have to start from the right and work your way left. So here's our binary number, 101111011. Let's group it up starting from the right. The first group is 011. The next one is 111. And what's left over at the end? Just 10. Now we translate each chunk. 011 is a 3, 111 is a 7, and 10 is a 2. Put them all together and you get 273. And just like that, you've translated from binary to octal.